Okay, hello everyone to today's seminar. So for today, we are going to have a presentation about the approaches for hydrometeorological cascading hazard assessment, a case study in the tropical region of the Northern Andes in Colombia. So in recent decades, tropical mountains regions have experienced devastating disaster caused by a series of hazards, including landslides, detritus flow, and floods. While these are effective hazard assessment methodology in place for each of these hazards individually, there is still a significant gap in our understanding and evaluation of multi-hazards. The complex interaction of these various processes in time and space can result in amplified and widespread damage. Despite the challenges, evaluating cascading multi-hazard is a crucial step toward reducing disaster risks and management urbanization to reduce exposition. In this presentation, we will examine various methodologies for assessing hydrometeorological hazard in complex multi-hazard situations. Additionally, we will explore a case study that demonstrates how cascading hazards assessment can be performed using several physical-based models in succession while accounting for the interrelationship between different hazards. This adaptable methodology provides user with significant control over its interaction and can be employed in a variety of environments with varied levels of data quality and quantity. And for this presentation, we have with us Maria Isabel Arango. She's a PhD student in Natural Hazards Working Group of the University of Potsdam in Germany. Her main field of research is hydrometeorological hazards evaluation and modeling, with an emphasis on multi-hazard and tropical environments. So please join me welcoming Maria.
Thanks very much. Thank you, Daniel, for the introduction. So, okay, I will give you today a very general overview of my main topic of research, which is hydrometeorological cascading hazards. And I will show you, I'm sorry. I will show you first, I will give you an introduction of the specific set of cascading hazards that we're gonna talk about. I'm gonna give you a very broad overview of integrated models, which is like a tiny part of the research that is being developed right now in this multi-hazard assessment. And we're going to review a case study that I worked on a couple of years ago in Colombia. Okay, so we will be focusing here on this specific set of hydrometeorological cascading hazards that occurs in mountainous regions. So in these mountainous regions, sometimes very intense rainfall episodes occur. Usually these rainfall are anchored by the effect of mountains. So many times a mountain blocks a pressure system that comes and then creates a very intense rainstorm. This rainstorm, sometimes when it's very intense, it triggers a lot of landslides over a region. These type of events are usually called morle. They are multiple occurrence regional landslide events, and they have been described in many areas of the world. So it's basically like clusters of landslides that occur in a mountainous region. But the unique feature of these cascading hazards is that at the same time that these landslides occur, when you have certain mountainous regions with a lot of rivers, that these channels or rivers get flooded. So they usually get flash floods. So they have a lot of energy, they have a high slope, so they travel downstream with a high speed, with a lot of water because it's raining a lot. Sorry. And then when you have these these clusters of landslides, and the soils are very saturated, they behave like debris flows. So you have these debris flows flowing in the slope, downslope, and getting into these channels. These channels start gaining a lot of energy, a lot of erosion energy, a lot of power. The amount of sediments start growing. The sediment concentration increases a lot, so it also increases the power of the energy of erosion and the power of destruction. Very often, these events kind of final end in populated areas. So these events are very, very destructive, because what you have in the end is a surge that travels downstream with a lot of like very large boulders. For example, it has an enormous destructive energy, and it happens very quick. So I will show you some cases. This happened in Colombia in 2017 in the city of Mocoa. And can someone confirm if you can see my pointer here?
Yes, we can see it.
Okay, perfect. So in this area, there was like a whole neighborhood of the city, and it got completely destroyed. You can see here the outcome, and more than 300 people died. There is another example here in Zimbabwe, a result of the cyclone Idai in 2017. Very similar chain of events, lots of landslides that occurred over this area. Then the landslide traveled to the channels, and then the channels finally landed in populated areas. Also, you see that the event not only finished here, but also it created like large floodings in rivers. And this is another case from Haiti. This occurred in 2021. And this was a very unfortunate chain of events, because it had rained a lot during in this area, but then also an earthquake occurred. So the rainfall already conditioned the soil, and then the earthquake in reality triggered this event. But it's a very similar setting. So you have landslides coming into flooded streams and then traveling downstream. In this case, this event was not very mortiferous because it was in a natural park, so not a lot of people lived around there. But if there was people in this area, it would have been very disastrous too. So we see that these events are very, very disastrous. They are very important to understand. Nonetheless, doing a quick research on the topic, you will see that usually they are often undocumented or documented improperly. So, for example, this is the picture of Mocoa, the case of Colombia that I showed you. If you see the Mocoa event, you will see that sometimes it's in the news or even in papers, it's regarded as a flooding or as a landslide, when in reality what happened was a combination of both worlds. They also, because they focus a lot in tropical regions, they occur in remote or undeveloped regions, which makes them to be not so notorious to the public and also not so studied. And they are not analyzed as a whole, so modeling them is a challenge, okay? Sometimes when you see like a land use plan or like a hazard map of a city or a populated area, and when they are trying to, let's say, assess the hazard of this type of multi-hazards, you will see that it depends on the professional who carries out the analysis. So if you ask a geologist or a geotechnical engineer, he will probably model the susceptibility to landslides or the hazard to landslides. And then if you ask, like, for example, a group of civil engineers or hydrologists, they will often model this as a flooding, when in reality, none of the outcomes, like the single hazard outcome, will be reliable, because in reality, this is a combination of several processes. So these type of events have a lot of challenges. So they have problems with the documentation, they have problems with their understanding, they have with their definition even. But for this talk, we're going to talk about the main challenge, which is modeling. Okay, how do we model this sequence of cascading events? Modeling is very important, because if we want, for example, to improve the land use management. For example, we want to avoid cities or towns to be located in this area susceptible to these events. Or if we know that already an area is susceptible to these events and we want to create measures, or if we want to know a city that already hasn't had any type of events of this type, but then we don't know with climate change how this hazard will change, then we need to model, okay, these events. And this is also a picture from a very similar, from another event of cascading hazard in Venezuela in 1999. Okay. So this is such a like an schematic view of the models of the event that we want to model. There is some growing field that it's the integrated models to model these events. So these integrated models, what they try to do is that they try to model everything, like all of these processes. So first we have like 3 big processes. The first one is we have landslides that occur in a slope. The second is that we have debris flow. So the landslide travel downstream or downslope, okay? And finally, we have a flooding. Usually, up to now, these events have been modeled, let's say, in 3, like separately, like this way, okay? So we model landslide, we model debris flows, and we model flooding, okay? But as I already said, it's a combination, so it's like very tricky. And also, if you kind of understand these processes in such a separate way, you also are ignoring that it includes many other processes, okay? So you have to include the runoff, the failure, the infiltration, the evapotranspiration, the rainfall, the entrainment of sediments, the position. So you have a bunch of like factors that play. So you can already like give an idea of how these events could behave. Also, there is this big factor that is that this event occurred in a it's a combination of a bunch of stuff that occur in a very short period of time. Okay, so these events are very fast, and they, for example, include some, I wouldn't say random variables, but maybe like stochastic variables, like things that could happen. For example, a damming, okay? So a landslide falling into a stream and damming it. Or also damming of streams caused by wood material, or a channel kind of deviating because there is like a blocked bridge or something like this. So you have this combination of factors that can give different outcomes every time. So it's very complicated. So this integrated model, what they do is that they try to model all of these processes in one single model, okay? I will talk about 2 integrated models that are under development right now. So the good thing about this, like a multi-hazard hazard assessment, is that it's a topic that is very, very actual. So a lot of people is working on this, and there has been a lot of developments. And I will talk here about like the ones that I know the most, but I'm sure there must be already a lot more. So the first one is called OpenLISEM. This is a spatial model, so it's based on GIS for runoff, floods, and erosion. It's very complete, so it's the most complete I know so far. And basically, it's a model that integrates all of these processes into one single model. Okay, so you have a rainfall scenario, and it models like the hydrological conditions, so interception or drought or channel flow. And then you also have sort of like the slope or like the sediment models. So it models the slope failure, shallow landslides, the entrainment of debris flow into, for example, a river or different debris flows. It also models the erosion, and it finally models the flooding. So at the end, it gives you sort of like this map. So this map is, for example, flow height, but it also gives you sediment concentration in real time, flow height, flow velocity, etc. So you know in real time, let's say, how the flow is behaving. There are like different landslides, and then when 2 different landslides meet, for example, or when a landslide and a flood meet, then how the sediment comes into the stream and how it increases the sediment concentration and how this flow travels. Like, it's very complete. There is another second model called RAVA flow. This model, it's not so complete as OpenListen, but it's also pretty nice. It models the travel, or the run out of a flow, but then it also models how this, for example, how flow behaves if there is, for example, a river nearby, or if there are two flows meeting. Okay, the very new, let's say, new feature of these two models is that they don't only use one phase equation. So usually for debris flows or floodings, we were more using like single flow models. So there were models that sort of recreated the path of a flow of one phase. Okay, but these new models, they use equations like momentum and mass conservation equations for both liquid and solid phase, and they interact with each other. For example, these models can simulate when a debris flow comes into a stream and how this debris flow mixes with the stream and how this affects the velocity of the flow after they two meet. Okay, so these kind of interactions they model. So usually what it uses is a DEM and like the areas that the failure areas, the volumes, and it gives you at the end, for example, flow height, flow parameters, so viscosity, for example, and the change of basal topography. So you kind of know after the event how the topography will look. These models are really cool. So these integrated models are a big advancement in multi-hazard modeling. Okay, another thing that I have to say is like both of them are free source, so you can download them and like you can use them, and they have good documentation, I think. But here comes the big disadvantages that they have, is that they are very costly, although they are improving because they are all the time being worked on. First of all, because they model so much stuff together, you need like big computational resources. Also, you need a lot of data. So for example, these are the maps that you need, for example, to run OpenListen, like the minimum maps you need. But then when you look the documentation, in reality, there are more than 100 input maps. Most of them are optional, like the rest of them are optional, but still, the fact that they are optional, it doesn't mean that the model doesn't use them, okay? It means that they have, for example, standard values that they use, etc. So it's a lot of information that you need, and very precise scale also. And that it also needs a lot of time. So I use OpenListen for my master's thesis, and each run, for example, will take easily 2 days. So if you need to calibrate a study area and you need to run several times, you need to consider that it's gonna take a long time. And the second big flaw of these integrated models is that the user kind of loses control over the results or the influence of the parameters inside the models, okay? Because you have, for one run, you have one single output. So what I was mentioning about the stochastic processes. So you have the initial conditions and you run like the whole sequence of the events. And then you have just one single output that comes out of the model. But then several things could happen in between. So, okay, not all the slope stability was very low. The slope stability parameters were very low. Therefore, you triggered too many landslides. Therefore, your flooding was too big. Therefore, so at the end, you have this output, and then you have to go back and like really understand what failed during this big chain of processes, okay? Because this is the example of OpenListen. These red, blue, and yellow squares are all the processes that it models. So we're talking about a model that models more than 15 processes, okay? So it's very hard to understand in what part of the model something failed, or to understand what parameter, for example, is changing. The parameters are also a big topic here, and these gray squares show the parameters that are common to different processes modeling. So for example, let's take an example of porosity. So porosity influences the infiltration of groundwater modeling, but it also influences the slope stability modeling. That means that when you change for some reason your porosity values in your model, you get different results, but you don't really understand. It's hard to understand if these changes were caused by the changes of the porosity in the infiltration of groundwater or the slope stability. So it gets like a complicated game. This is still an amazing like field, and it's very promising, especially in areas with a lot of good information. So they have really nice like case studies where they have a lot of information. They have good data of several events, and with this, you can easily understand how good these models behave. The problem is like we don't really have this much information for many study areas. This is why we carried out this analysis. So this is an analysis that we worked on some years ago, but we published recently. Sadly, they were published in Spanish, but I will translate them here. Translate them here, yeah. So this case study is from Colombia. It's an event that occurred in 1990. It's a very old event. But even though it was very old, it was very well documented. The reason why it was very well documented is because it occurred in an area, in a basin where there was a hydropower plant. So after the event, this company did a very nice report on the event. There were like many good data. Also, we had really good rainfall data, etc. So the event occurred in a municipality called San Carlos in the Arenosa Basin, okay? So here comes the San Carlos River, and after the basin, it sort of traveled downstream to the town. So what happened in September 1990 is that there was a lot of rainfall that triggered thousands of landslides, like the density of landslides was crazy. All these sediments came into the channels, and the channel kind of eroded its own bed, like a lot. And you had these huge boulders, like the flow became so powerful and so like dense that it carried downstream very, very large boulders. So after the event, the basin looked kind of like this. And then this surge traveled downstream into the city. There was a lot of destruction into the town, let's say. Although by the time it reached the town, the flow wasn't so powerful. It was more like a flooding, but still like in this area, the destructive power of the event was quite big. So after the event, they took some really nice aerial photographs. Sadly, they couldn't cover the whole basin because it was still very cloudy. But we had enough data, so we could digitalize. So we digitized the failure points in black here. I'm sorry if it's not really visible, the failure points. We also digitized the debris flows, so the red polygons. And finally, we digitized the flooding area, which is here in blue. So we took this information as the ground truth to validate our models. So the methodology consists in, instead of using one of these integrated models that sort of models everything together, we used coupled models. So we used 3 different models. First of all, we modeled landslides with a model called triggers. After we modeled this, the output of this was used as an input to model the debris flow runout with a model called flow R. And the output of the landslide and the debris flow runout modeling were used to model the flooding with the model IBER. Of course, I have to emphasize that this is all physically based models, okay? So for this type of events, you also have all sorts of methodologies to evaluate hazards. There are empirical models, numerical models, but here we are focusing in physically based models, which are very like widely used for this type of these hazard assessments. So the first part was the slope stability modeling. So we use triggers, which is it's a very common model. It's it's a slope stability coupled with an infiltration model. It models only like shallow landslides, and it is not very good suited. It's not very well suited for deep-seated landslides because they assume an infinite slope model. So it doesn't really consider vertical forces, only horizontal forces, and it assumes a failure surface that is parallel to the ground. It's a transient pore pressure model. That means that on each time of the storm, you can analyze which is the safety factor for each cell. So it's really cool because you can see how the safety factor kind of evolves through time in the storm. And it's very nice because of course, it needs data, but it doesn't really like a huge amount of data. And it's pretty good because you can easily calibrate the model. So this is the good thing about using each model for separate, because you can actually calibrate each one, understand which parameters are better for this model, and then continue to the next one. So the inputs are the geotechnical soil properties. They could be homogeneous or maps. Hydraulic soil properties also, a soil depth map, which is quite important, and the rainfall scenario. I also need to include here, I'm sorry I missed it in the slide, that it also considers the initial conditions, initial saturation conditions of the soil. So the water table depth is kind of the most important parameter, which is also very hard to know because we actually don't know what was the water table depth before the event. So for this, we had to carry out like a calibration for this, pre-event hydraulic soil properties and the soil depth map, which we also didn't know. For the soil depth map, we use a fairly simple model that estimates the depth of the soil based on the slope and the kind of field measurements which we had. So the soil depth of the study area, we estimate between 1 and 2.7 meters. Although this is kind of one of the big limitations, because the event was so famous that there are several reports, for example, saying that the soil depth in some areas were larger than 20 meters. So this is a tropical area, very fast chemical weathering of rocks, and you have these huge soil profiles that can easily lead to very, very deep soil profiles. But in any case, the official sources we had were up to 2.7 meters. And the other factor that we had to calibrate was the depth of the water table before the event. So for this, we run the model several times, varying all the time the water table depth. And we found this is the rock curve. So this is the false positive ratio and the true positive ratio. So it's comparing like which cells are failures based in the model and also fail in the reality, and with cells that were compared like as stable in the model versus the one that were unstable in reality. And then we can find like the best performing scenario of water table depth, which is a meter below the, let's say, like the contact between soil and rock, which we assume is the failure plane. So with this data, the soil depth and the water table depth, we can model the slope stability. So these are the results. We have that the red cells are considered as stable because they have factor of safety lower than 1, and all the green cells are considered as stable. Okay, this is the scenario at the end of the storm. Okay, so everything that's red, it's supposed to have failed during the storm. Of course, this is a modeling, so this is a model, so it's not 100% accurate, but the results were pretty good. After this, we can continue to model the debris flow. Okay, so the debris flow runout. For this, we used a model called FlowR, also quite popular. It's a model that estimates the distance and the path of flows based on the topography and the rheologic parameters of this flow. This kind of models uses 3 different algorithms or 3 different sets of equations. So the first set of equation is like the routing. So basically it calculates where a flow will continue based on the topography. So it kind of looks for the cell that kind of goes down every time and says, okay, this is the most probable route. Then it has persistent algorithms, which is kind of determines the behavior of a flow if there's, for example, very sudden changes of the direction, for example. So when you have a flow, the logic, let's say the computational would be to have like a 90-degree 90-degree run out. In reality, this is not realistic because the persistent will not allow it to like take a 90-degree change. Okay, so this is kind of keeping the most realistic route of flows. And the third set of equations is the energy. So it basically tells how far will the flow travel. This is kind of an empirical model because it's independent from the mass volume. It relies more like on the potential energy equations, so it doesn't really calculate any volume. Because it's so empirical, it needs DEM. Of course, it needs source areas. So for example, in this case, they already give the input to the model saying like, okay, we are making this cell to fail, okay? For this, we use these results, okay? So we consider that each of these red cells will fail. And it also needs some flow parameters that are kind of need some calibration for it. So one of these parameters is the friction, it's the spreading coefficient, which is the most important one. So you can see here, they are varying the spreading coefficient, which is called Holmgren. In this case, you can see how the larger this coefficient becomes, the more the flow kind of spreads. And they're also kind of showing how the resolution of the DEM influences the results. And this is kind of cool because what they say is like when you find like a really nice combination between, or like a really nice trade-off between the spreading coefficient and the resolution, real results will be very accurate, despite of changing the spreading coefficient. So in any case, this needs some calibration. So it needs you to like run several times and kind of understand how these flow parameters behave in this study area. So for this, what we did is that we took all the landslides that occurred in reality in the event. So these are like the brown color here. I'm sorry, it's not really visible here, but the brown cells here are the failures. And then we calibrated these three parameters to kind of understand which are the ones that work best in this study area. So for example, you can see here that this is a very low friction coefficient. So this flow didn't really travel that much downstream because the friction was too high, for example. Or how a high spreading coefficient makes the flow kind of spread too much. So when we model this around 50 times, the good thing is that this model is quite fast. And then you can find like the optimal combination of flow parameters. We say, okay, this kind of models the real event in a realistic way, okay? But because we are really trying to model these source areas, like the modeled ones, then we run these areas with the calibrated parameters and we get this result, okay? Another cool thing about this model is that actually the result that it gives is in terms of probability. So what it does is really like, it models many times the same source areas. It models like several times, you can control how many times. And at the end, they say, okay, the most likely path, for example, here, the red color means that in this was a path that repeated many times in many simulations, while the other colors show that this was not such a likely path. So you at the end, you have like a probabilistic approach. What are the most likely path of the debris flows? So here you can, for example, see that, I don't know, areas with a probability larger than 50%, you can easily recognize them and then say, okay, these are the most likely debris flows that will be triggered by the landslides. After we have this, we can come to the third part, which is the flooding, okay? So for the flooding, we use a model called IBER, which is a very also common model for flood hazard or flood susceptibility. It's a two-dimensional numerical model, so it only like, yeah, it doesn't really take into account like the depth of the flows. And it uses shallow water equations. So this is important. So the integrated models that I talked before, they take into account the solids, like the sediment and the water, okay? But this model only models water, okay? So it doesn't really take into account how much sediment there is in the water, which is a very big limitation of this type of models. And what it uses is a hydrograph, so basically the flow of water at each time step, a DEM, and the properties of the soil, which basically dictate the roughness of the soil, so the land cover, etc., and the roughness. So basically what we have is, okay, we know the rainfall event because we had a rain gauge. The event lasted approximately 8 hours. We have the rainfall, which is this clear blue line. Using the curve number or like, the shape of the different parameters of the shape of the basin, we can calculate a concentration time. And with that, we can turn this rainfall into a hydrograph or like a constant, a liquid flow, which is like this dark blue line, okay? And we also have a curve of solid flow, because from the slope stability model, we know at each time of the storm how much volume of soil failed, okay? And with this, we can assume that within certain time, these sediments that fail, they reach the streams, okay? Because we already checked in the debris flow runout that actually these runouts reach the streams. So we can translate this volume of solids into also a curve, and we can calculate a final hydrograph, which is this blue and brown bars. And this black line is the concentration of solids, okay? So we have a concentration around maximum, it was like 35% of sediment concentration, which is very low, because usually these flows at the end became sort of like a hyper-concentrated flows, which can branch up to 70% of concentration of sediment. So these kind of models have some limitations, of course. And with this final hydrograph, we can finally model the behavior of the water and the sediment coming out of the Arenosa Basin, which is here, and how it traveled downstream into San Carlos town, which was here, okay? So here in blue, you can see the real extent of the flooding, and these green to red colors show the modeled extent. So you can see that this model actually under-predicted the volume of water and sediment flowing downstream because it has some limitations, okay? Mostly the limitations are based on the fact that we cannot really model the erosion of the river, the sediments of the river, because we only are taking into account the sediments coming down from landslides, for example. So no erosion from the river. Also some limitation, it's about the time that it takes from sediments to travel from the source to the streams, which we also don't know. And these questions, they are all solved by integrated models. So integrated models, they include all of this. But now this is the moment where you have like a big trade-off between, okay, do I really want like a very, very nice and detailed model, which needs a lot of information, a lot of that which I don't have, or do I prefer a more general model, which will give me kind of not so precise results, but it kind of, I have like more control to understand how it works, and like it doesn't need so much information, okay? So this is the trade-off. So in conclusion, first of all, the cascading hazard assessment, it's a very important field and it's evolving very fast. So if I'm sure, like I did this work, I don't know, some 2 years ago, I'm sure right now there must be a ton more models, ton more information, more research. But it's nice because it's a very important thing to work on. And this methodology of coupling different physical models for modeling cascading hazards have some really nice advantages. For example, it has more control from the user, so the user can see the influence of the parameters in the output of each single step. Also, it can see the outcome of each of the model and then see how that influences the whole event. And it gives a better understanding of intermediate processes and how they relate with each other. It has a faster implementation, so it's an easier implementation, so it's faster. It needs less input, still needs quite some input, but way less than integrated models. And it's flexible because, for example, today I talk about 3 specific models, but there are so many models that you can use, freely available, with license, empirical, physical, numerical, and you can play with these models, coupling them in different ways. But the disadvantages is here you have to have a trade-off between precision and accuracy. So what we all want when we model is we want precise and accurate results. Okay, so we really want the results to be as stick to the reality as they should be. But then we also have some results that are not accurate, not precise, so not really stick to the reality and not really true with each other. But then we need to play with this. Do we really want accurate but not precise, or precise but not accurate? And the problem with this coupling of different models is that they are less precise, okay? And I think the integrated models kind of are very precise, but it's difficult to really get accurate results, I think. So, for example, this coupling of models is not really suitable if you are in a completely new area where you don't have any way to calibrate the models, because otherwise you're also kind of making the information up. The connection between hazards is sometimes unknown, or it gets lost because the models sometimes they don't really couple so well. And also the fact that, to use these methodologies, I had to basically learn 3 different models, packages, different different ways of running the packages. It's very time consuming, but this is kind of what we have so far. And I think with this, I finished. Do you have any questions?
Okay, Maria, thank you very much. Any question here in the room? Any question online? The people online, you can just raise your hand and I know, to give you the mic. So any question here? Okay. You? Yeah. Give me a moment. I will be there.
Hi, can everyone hear me okay? Thanks for the great presentation. I was wondering, so you were talking about the trade-off between doing these physically coupled models versus integrated models. And I'm wondering if you could comment on, do you think because they give kind of different information, it would be worth doing both? Or is the effort to do that just not worth it in terms of the results that you're going to get?
Yeah, so this is a good question. Let's see if I got it right, because the audio sometimes was not so good. So your question is if I think it's worth to kind of do both approaches, integrated models and coupled models in the same study area, for example.
Yes.
Yes, or if you have an unlimited amount of time to do, that I think that would be like the best, of course, like if you are hired to create a hazard map, it's the optimal thing is to kind of try everything, okay? So you can try empirical models. Of course, it depends on what type of information you have, the amount of information, the quality of information. But yeah, the more you do, the best. But it also takes a lot of time and a lot of effort because it's different models, different approaches. It's like it's learning a lot. So basically that's what I did. Like I tried different approaches and this is what I could conclude. Like this is my view of like the advantages of this or disadvantages of both approaches. But yeah, I mean, there is not really like the best option. It's just a trade-off you have to do between the two approaches. Like, but yeah, if you can, of course, like it would be the best. And then it really gives you an idea of really what factors play a role in each study area and which event. So yeah, like as a research exercise, it's very useful. But yeah, when you really need to apply it for a study area, like in a more efficient way, it gets kind of tricky because it's a lot.
Oh, thank you.
Maria, I have a question, which is I know how good geological engineer you are, and I wonder how those geological features, for instance, in those kind of tropical environments where you have really weather soil impact this model, or how those features are sometimes overseen by these models.
Yeah, so I think yeah, so I think it depends on the scale of your analysis. So maybe I'm wrong, but maybe within the maybe what other engineers work in is like very specific sites. Okay, so you do like the slope stability of one slope, for example. In this kind of analysis, which is very the scale is very detailed, these geotechnical properties, for example, play a huge role. Okay, so changing the geotechnical properties of for modeling one slope, the stability with this finite elements model, for example, it's very crucial. The good thing about these regional models, like GIS based, so basically you are kind of analyzing the slope stability of each cell of a grid. What they have really cool is like, it doesn't really matter the value. Of course it matters, but at the end, what you have is sort of like a comparison between the slope stability in some areas versus the other ones. So for example, given a factor of safety in a regional map, it's quite tricky because you know that the geotechnical properties of each cell vary so much. Even if you have like a really nice sampling, like you know that geotechnical properties change within a very small distance a lot. They could vary a lot. But because you have other information, for example, the slope, the curvature, the land cover, etc., you can at least get an idea of which are the most susceptible areas within that area, okay? And because you analyze a large area and you have very different values of like slopes, etc., you can get like a better idea of like where is the most critical area located. But this analysis is not so good to really like find, for example, the exact factor of safety of an area. I don't think it's so good. So the answer is this regional model allow like more like less detailed information, geotechnical information. So you have space for more generalization. So in general, I don't know, it depends, but geological map 1 to 25,000 or 1 to 10,000 scale is good enough. Like it depends, of course, on the study area. But if you are using a DEM that it's 10 by 10 meters, which is very difficult to improve, then it's enough. But of course, you need some information. But they allow space for more like generalization, I think.
Okay. And my final question is about the implementation of this kind of technology I mean, these technology are useful if they help us to prevent any kind of disaster, if possible. But at the same time, this information, this kind of modeling requires a lot of data and a lot of information. So what do you think is like the possible path to get, I mean, the trade-off between how can we get good value of this to prevent disaster, but without sacrificing the accuracy of the model?
Yeah, I think these regional models should be very much focused on land use management. So more like prevention, I think. So because when you have already like a city with bridges, with already like constructions in rivers, everything gets very complicated and you need more detailed models usually. Like when you are in a urban area, already a 10 by 10 DEM, it's not enough. Like you have bridges, you have a box culvert, etc., that changes everything. But when you are doing like a general analysis for example, a municipality, and you want to kind of know which areas are in risk or have high hazard, this type of analysis is super useful, like to already kind of define critical areas which you know they should not be urbanized, which in some countries it's already like a problem. Like in more developing countries, these areas are being urbanized all the time. So these type of general analysis are very useful, like basic studies. Like first, it's like the first analysis you carry out in an area where kind of it's unknown. And then with this information, then you can say, okay, this critical area, then we can do like a more detailed analysis. That it's not a regional analysis, it's detailed, and then you go and then you do field survey, and then you get like a better DEM. You know, you kind of improve this. But this tool for me, it's more useful like at the beginning of the land management. But this is the hardest, like to get to, especially developing countries, to care about this before they have to urbanize an area, for example, it's tricky.
Okay, Maria, thank you very much. And yeah, see you all next week.
Thank you very much.